Welcome all of you. Today I will discuss that solution chapter, that is colligative property we have discussed last class. In that we have already discussed the colligative property which depends on the number of solute particles of the solution, not on the nature. So today we will discuss this colligative property that we have discussed in last class, that is lowering in vapor pressure. But today I will discuss about the elevation in boiling point is a colligative property, and its elaboration and explanation etc. Elevation in boiling point. So at first, you listen please. At first, what is boiling point? You know boiling point, the temperature at which a liquid boils. What is that temperature? And here we relate it with the vapor pressure. So when the vapor pressure of a liquid is equal to 1 atmospheric pressure, then that liquid starts boiling. Some liquid at room temperature may evaporate, and these liquids are called volatile liquids, and some are non-volatile liquids. What about the volatile liquids? Means volatile liquids has vapor pressure more than that of the atmosphere pressure. So when they are exposed to atmosphere, that volatilizes at once. Like your spirit, acetone, etc. When you open the spirit bottle cap, that will remove from the bottle, and automatically the bottle will vanish after some, if there is no water, if that is pure spirit. So the volatile liquid, non-volatile liquid, etc. are there. So in general, we can say when the vapor pressure of a liquid is equal to 1 atmospheric pressure, means atmospheric pressure means 760 millimeter of mercury is taken into account, then it is said to be the boiling point. So if the temperature, the boiling temperature, the boiling point related to vapor pressure of a solution, or vapor pressure of a liquid. If that's so, vapor pressure of the liquid and vapor pressure of the atmosphere decide what should be the temperature of the liquid. When a liquid is at surface, means on the earth's surface, or at the sea level, at that point we can say the boiling point of that liquid means that liquid is that when the atmosphere pressure in that sea level, we know the atmosphere pressure is 760 millimeter of mercury, means 1 atmosphere pressure. So the vapor that removed from the liquid may not be that one. So we have to heat the liquid to have the vapor pressure equal to 1 atmosphere pressure. Let's say consider water. You know the boiling point of water at 1 atmosphere pressure is 100 degree centigrade or 373 Kelvin. But not always. If you take that water to the top of the mountain, then what will happen? The vapor pressure of the water, something more, because the atmosphere pressure is less. Atmospheric pressure at the top of the mountain is less, so we need lesser heat, or we need lesser temperature to boil up that water at that top of the mountain. So the atmospheric pressure plays vital role to decide what should be the boiling point of water. So at the top of the mountain, when water boils less than 100 degree centigrade, so if you try to cook there, it is difficult to cook it, because the boiling point of water is something less than 100 degree centigrade, where the cooking material remain unboiled there. The cooking material remain unboiled there. So it is very effective. The boiling is very effective at the sea level or at the surface of the earth. So here is a relation, very good relation between the vapor pressure and that of the boiling temperature. If the atmosphere pressure and the vapor pressure or the boiling temperature, if atmosphere pressure is very high, then the boiling temperature will be low. So atmospheric pressure, if very high compared to the vapor pressure of the liquid, then we need higher temperature to boil up that liquid. The boiling point is more. So now, the vapor pressure, depends on the surface area. When there is a pure liquid or pure solvent, and we are considering in this is solution chapter, we are considering about the solution, very dilute solution. The dilute solution and the liquid, when a volatile or non-volatile solute is added to the solvent, then it becomes a solution. The solution of the boiling point of the solution always higher than that of its pure solvent. Is it clear? The boiling point of solution always higher than that of the pure solvent. That is why we are saying elevation means something higher boiling point, correspond to something higher boiling point of the solution. So what is the cause? Then cause is obvious. When a non-volatile solute is added to this solvent, the vapor pressure what is there at the pure solvent will be less in case of solution. When the vapor pressure becomes lesser, then we need higher temperature to equalize its vapor pressure equal to 1 atmospheric pressure. So when 1 atmosphere is there, the vapor pressure of the solution lowers down, so we need higher temperature or a higher heat. So we have to hit more temperature, at more temperature. Therefore, the boiling point of solution is always higher than that of the pure solvent. That is why this elevation in boiling point. That is why this elevation in boiling point. And we are considering the elevation in boiling point is a colligative, we have to prove it. Again, here we know the boiling point when the vapor pressure, lowering in vapor pressure is high. If there is much lower in vapor pressure, then there will be much higher in the boiling point. Boiling temperature, much higher in the boiling temperature. So they are directly proportional. And from the Raoult's law, we know del P proportional XB, mole fraction of the solute. So directly we can say XB del TB is directly proportional to XB. Here, elevation in boiling point. Elevation in boiling point is directly proportional to mole fraction of the solute, means elevation in boiling point is a colligative property. So, this is the observation, and this is the Raoult's law, and this is the conclusion. The observation says much lower is the vapor pressure of the solution, much higher is the boiling temperature. Because we have to equalize with the atmospheric pressure. So this is the experience, and this is the law, and this is the conclusion. And to have this one or this relation, to have this relation again, the experience, we can also establish by drawing the vapor pressure and temperature curve, boiling temperature curve. How it is? Let's say the pure solvent, this is the vapor pressure curve of the pure solvent, and this is the vapor pressure curve of the solution 1 containing some non-volatile solute. This is the solution 2 containing another amount of non-volatile solute, more amount of non-volatile solute. So here the pure solvent has vapor pressure P0, let's say, and T0 is the, and let's say this is the 1 atmosphere pressure. Let's say this is the, let me draw again, this is the P0 and it is 1 atm, 1 atmosphere pressure, 1 atmosphere pressure. Then that means the atmospheric pressure is there. The solution has to have same vapor pressure as that of the 1 atmosphere pressure. Solution 1 and solution 2. If it is 1 atmosphere pressure, then the temperature related to this is the boiling point of the pure solvent. boiling point of pure solvent, and this is the boiling point of the solution 1, and this is the boiling point of solution 2. And here the relation can be established by considering two triangles ABD and ACE here. These two triangles are congruent because of same angle. Here these two angles are same, this is the common angle, and these two again will be same. So according to this, these two congruent relation triangles can give the relation as AB by AC is equal to AB by AC is equal to AD by AE. AD by AE. This is the relation between the two congruent triangles. AB, what is the value of AB here? AB here you can say this P0 and 1 by are nearly same. So these two may be related as P0 minus P1. And this is P0 minus P2. Let's see. For dilute solution, this will be same as. And here AD is the T2 minus T0. And AE is equal to, AD is equal to T1 minus T0, here T2 minus T0. This is related as del P1, and this may be written as del P2, and this is del TB1, and let's say this will be del TB2. So from this we can say del P1 by del TB1 is equal to del P2 by del TB2, and from this we can say del P in general del P by del TB is equal to constant, and here we can write del P del TB proportional del P. This relation can be taken out from that, and from Raoult's law we know del P is equal to proportional XP. So here we conclude del TB proportional XP means elevation in boiling point of a solution containing non-volatile solute is directly proportional to mole fraction of the solute. As it depends on mole fraction, we can say it is a colligative property, or we relate with the molarity as, let's say here we can write del TB is equal to K, one constant XB, and here XB can be related as NB, or small n you can write for the solute and capital N for the solvent, small n plus capital N. Here K, for very dilute solution we can minimize this one to capital N only, because N plus N for very dilute solution nearly equal to N. Nearly equal to N. So N means number of moles of the solute, that is double by molecular mass, and here capital double by molecular mass. This is solvent, this is for solute. Now I can rearrange this as K dot double by M into capital M by capital W, delta here. Now K M by 1000 W by M into 1000 by W. You can rearrange this one like this, and this may consider as another constant that is called Kb, and this is called molarity of the solution, let's say M dash, molarity of the solution. So here del Tb is equal to Kb into M dash, elevation in boiling point direct proportional molarity. So here you can write del Tb proportional molarity of the solution. As we have discussed, the property of the dilute solution which depends on the number of solute particles, or the number of moles of the solute particle, or the molality of the solution is called colligative property. Here the elevation in boiling point is a colligative property we have proved. Now from this data you can easily calculate molecular mass of the solute, non-volatile solute, from this relation. That relation you can directly calculate as del Tb is equal to Kb M dash and you know molality means small w by small m, 1000 by capital W. Here this is the weight of the solution, weight of the solute, molecular mass of the solute. So the molecular mass of the solute is equal to 1000 kBW by del TB capital W. This is the relation from which molecular mass of the non-volatile solute can be calculated. Here km by 1000, that is Kb. This Kb is also called Moolal elevation constant. Moolal elevation constant or so-called ebuloscopy constant that has a particular value for a particular solvent. Ebuloscopy constant. So the molecular mass from the elevation in the boiling point can be calculated, and elevation in boiling point is a colligative property can be proved. Why there is elevation in boiling point, I have already discussed. These are all the summarized facts about the elevation in the boiling point, that is a colligative property. Next class we will discuss about the freezing point and osmotic pressure. Let's stop. Thank you.